Okay, hi everyone. This is the first talk in our seminar in this semester. So it's a great pleasure to have Professor Yue Yu from Lehigh University. So Professor Yu received her PhD from Brown University in 2014, and after that she was a postdoc fellow at Harvard University. Then she joined the Lehigh University as assistant professor and got promoted as associate professor in 2019. Her research lies in the area of the applied and computational mathematics, with recent project focusing on non-local problems and scientific machine learning. She received two very prestigious awards, including NSF Career Award and the Air Force April Award. So, yeah, please.
Yeah. Okay. Yeah. Thanks a lot, Professor Lai, for the nice introduction. So yeah, and first I want to thank organizers, Professor Lai, for this kind opportunity and to present here. I feel truly honored to present in front of so many experts in the imaging data and the optimization. I'm sure you guys can give us lots of advices, can help us to improve our model. So yeah, so today what I'm going to talk about is our work on learning a non-local operator for heterogeneous material modeling. So here, yeah, so firstly, I want to emphasize that although the main application I'm going to focus today is on heterogeneous material responses, but however, this approach actually, it can also be applied to other data-driven problems, can be applied to generally for the modeling of any complex system behavior modeling. So yeah, but however, but in the form of the heterogeneous material responses, then I'm going to formulate our learning problem to two types, from simpler to say more complicated. So the first one is, well, when we are interested in the complex system behavior, but say we are interested in a homogenized surrogate. That means, well, we are interested in the global behavior. So then in this case, we propose to learn a non-local surrogate as this homogenized model, as a coarse-grained model. And then the second type of the more complicated problem is, well, when the material heterogeneity cannot be neglected. So then in that case, we propose to leverage our learning. So basically combine the non-local model with the neural network and learn a non-local solution operator or non-local neural operator. Okay, so yeah, so then since we are going to talk about so then in the form of the heterogeneous material response modeling, let me try to for you guys to see the motivation of our two models. Let me try to introduce three exemplar problems. So firstly, for you guys who haven't been heard about heterogeneous materials, so what is the heterogeneous material? Well, scientifically, that means the material has heterogeneity in strength from one region to the other. So here is one example. We have a heterogeneous bar. So this bar, you can see that's maybe like a composite bar. So you have two types of the components of that. So these two types of components, they have they take different layers. So it's layer by layer. And then we are interested in the behavior of this heterogeneous bar. So in this particular problem, we are, for example, interested in if I have a projectile hitting one end of this bar, then there will be, of course, generate a stress wave, a wave pulse is going to propagate along this bar. So then this wave pulse is going to attenuate and change shape when it encounters the interfaces. So our question is, when this bar is very long, so when we are trying to know, say, very long-term behavior of this pulse of the pulse propagation, how should that be like? So for example, here my layer size is 0.2, but the total length of my bar is hundreds or even thousands. So there's actually thousands numbers of the interfaces. So in this particular application, we can see that in the heterogeneous material modeling, well, you have very small scale dynamics and the interactions. So that might change your global behavior. So in this first example, one property we can see is, well, we don't really want to resolve all these small, the layers, but however, we are interested in the global behavior. So in this case, we say, well, we want to find a homogenized model for it. So then the second example problem is a little bit more complicated compared with the first one. So, but however, that probably should be closer to our life. So this comes from, I mean, I don't know how many of you guys have the terrible experience of, like, say, dropping your iPhone and then start to have a crack on your iPhone screen. So what is your iPhone screen made from? It's a material called glass ceramics. So glass ceramics is one type of the glass which contains the volume fraction of the randomly distributed crystal grains in a glassy matrix. So here, what I'm showing is two examples, kind of the lab observed microstructure of the glass ceramics. So here, the light green represents the crystal grains, and then the dark gray represents the glassy. So the glass ceramics is better than the conventional glass material because it has superior material properties, such as it has better fracture toughness. I mean, so basically your iPhone is less likely to have a totally broken screen. But however, as you can see here, when you have different fraction of the glass of the crystal, or when you have different microstructure, then the crack pattern is totally different. So that means, well, if you're interested in, for example, design a better material of the glass ceramics, then I need to study this crack pattern for different microstructure. That becomes like really non-feasible, because each simulation you need to resolve all these small structures, and that takes a really long time, like 72 hours, for example, in this particular problem to simulate one microstructure. Okay, so now let me try to even leverage my problem to an even like harder one. So this problem actually comes from my collaborator from the mechanical engineering. They run a wet lab. So what they are trying to do is they want to predict the behavior of a heart valve leaflet tissue when they implement that into the human body. So basically, what you are seeing here is a real heart valve tissue. I mean, that's from pig, and then they mount that to a biaxial testing device. So then you see these 4 clips, they are trying to stretch this tissue, and they have the digital image correlation technique. So that's the green grids here, trying to record the displacement, the location of each point of this tissue. So basically what they are interested in is, well, when you are implement this heart valve tissue into the body, when it's subject to a new load, maybe you've never seen before in your lab, then what is the material response? What is the deformation of this tissue? So this problem is more complicated because, firstly, this material is highly nonlinear. It's anisotropic, meaning that, well, there is a fiber like embedded in the matrix in this tissue. So then the fiber orientation also differs from different subregions, and even more severe. Without damaging the tissue, there's almost no way for you to know what is the exact microstructure of this tissue. So therefore, even the microstructure is unknown. So classically, how people do that? Well, usually we just try to assume a conventional, like the phenomenological model for that. And then we assume that the material it's a homogenized one. So then we try to fit the parameters of this conventional constitutive model to the stretch stress curve of this lab test. However, because you neglect the heterogeneity of the material, so therefore, usually we see the displacement error is relatively large. It's like 10 to 30%. Okay. So after seeing like these 3 exemplar problems, I mean comes from the material modeling. So then what are we trying to? So then I'm going to firstly trying to give you one of our dessert property in our development. I mean and also the kind of the key idea underneath our development. So basically from these tasks, one see like 2 general dessert properties. So the first one is, well, we hope that our learning model can be generalizable, can be usable to future prediction tasks. So that differs from some of the, neural networks, for example, like the popular pins, it's trying to mimic the finite element solver. So then basically, if you have a new loading, you need to retrain the neural network. But here, what we hope is we don't really need to retrain the neural network. And that means, when we have the model, when we have the neural network, like say from our heart valve tissue, then when you implement that to a new loading, it's still applicable. And then the second property kind of comes more from the mathematical, the numerical PDE background. So in numerical PDE, we are interested in the well-posedness of the problem. Right. So then for here, we are still interested in the well-posedness problem, but instead that's the inverse problem. So that means, hopefully our problem, of course, can be maybe like say identifiable, our inverse problem. And for the problem, and even if we couldn't like really show its identifiability, maybe hopefully we can still try to make sure it's less likely, prone to problems like overfitting or maybe like say vanishing gradient. At least we hope that our developed data-driven model is stable. And then another property comes from like say what we usually kind of want from the numerical PDE solver. For numerical PDE solver, if you try to solve a PDE, you build the grids on this computational domain and you get a solution. And then you try to refine your grids. Then you hope that your solution from these refined grids should be consistent, with the previous one, or even you hope that you can have a better accuracy when you try to refine the grids. So here we are still hope we can get such property. So that means, when you change the resolution, so here is maybe the observation resolution, then your model can still be applicable, can still have some consistency. And even better, we hope that when you refine the observation resolution, then you can have some convergence. So in the classical neural network, here I want to emphasize that this is not easy. So because, for example, if we try to simply use a classical neural network to model our problem, so here F is the loading and the different xi are maybe different material at different points on the domain. And here U is the displacement we are looking for. So here, the classical neural network can be seen as basically a mapping from a vector to a vector. And then first you lift your input to some feature, to some high dimensional feature, and then for example, when you are using a kind of a simple MLP, then you have you are going to have the kind of interactions between different between different material points of these features. But however, if you try to change your resolution, then all these parameters, they are not applicable. You just need to retrain. But so therefore here, one of the repeating thing that I'm going to, the reason why I'm trying to use the non-local operator is, if you try to parameterize this interaction of the neighboring materials, like maybe in the feature layer, and then possibly you can try to reuse that. So one idea is maybe you can parameterize those kind of the strengths of the interactions with, for example, in the polynomial space, or maybe parameterize that with a neural network as a universal approximator. Then you can reuse that when you try to change the resolution, because you can still have an approximation of the strengths of these interactions. So that's how the integral operator or the non-local kernel can help us. So now let me try to start from our simpler problem. So that's the homogenized model. Sorry.
Can I ask a naive question?
Yeah. Please.
So in this problem, do you assume the forward procedure, there is some modeling or like a PDE, or you don't really assume anything, just purely data driven?
Yeah, that's a great question. So for the first type, we do assume an underneath PDE form. So basically, we are just learning the kernel. So the PDE, or that's actually an IDE, is given by this non-local problem. But for the second one, we assume that the PDE form is hidden. we don't really know what's the PDE form. So it's more general.
But you assume this is a special type of PDE, then this kernel, I mean, basically the solution can be written as some kind of kernel integral with some kind of kernel, or not any PDE can be written as some basically convolution or something, right?
Yeah, that's a good question. So the answer is actually we can prove that as far as your PDE solution. I mean, for the first type, of course, it's restricted, but for the second type, I mean, I'm going to cover more for the second type. So when you try to combine that with the neural network, it actually can be shown that it's a universal PDE solver. So that means as far as you can find a fixed point and the solution proceed to your PDE, then I can show that my approach, this integral operator, is a universal approximator.
I see. That's fantastic. I'll let you explain more. Thanks.
Yeah. No, that's a great question. So yeah. So thanks a lot for asking that. Yeah. So okay. Yeah. So the first one is, I mean, yeah. So let me start from simple. I mean, and more maybe like say more restricted form to more complicated one. So firstly, the simple one. Let's start from what is a non-local model. So maybe because I know maybe many people here are not so familiar with the non-local model. So for the non-local model, the underneath assumption is each material point is interacting with, like, say, a neighborhood with some distance. So of course, this distance can be, like, say, on the whole domain, or for example, what I'm showing here is it can be interacting with a region nearby. So like a sphere, like characterized by the distance delta. So the comparing with the classical PDE, this non-local PDE has some advantages. It can capture some effects the traditional PDE cannot capture. So firstly, it's actually can be, and because it kind of trying to collect the behavior of a neighboring region, so therefore it can be used as a good homogenized surrogate. It can capture the multi-scale behavior. And the second property is because it uses an integral operator instead of the derivatives. So therefore the solution allows like more singularity. So for example, like a singular solution or discontinuous solution. So that helps, like say in the problems when the solution has discontinuity, like in the crack problem, or like say when it has anomalous behavior, like subdiffusion or superdiffusion. Here we are going to focus on the first property. So that is using the non-local model as a homogenized surrogate. So how does the non-local model look like? So for this one, we are actually having an assumed form of our underneath model. So our model looks like this. So here the U is basically the material displacement, F is the loading, and then usually you have the divergence of the stress tensor here, but however here we replace that with a non-local operator. So here you can see each material point is interacting with its neighborhood with the characterized by the distance delta. So here the K, what we call the non-local kernel K, characterize how this material point is going to interact with its neighborhood. So therefore, as you might imagine, well, when I have different heterogeneous bar, maybe when I change my material, change my layer size, then the homogenized behavior is going to be different. So where should we reflect that? That will be reflected in this non-local kernel. So this non-local kernel is actually microstructure dependent, application dependent. So yeah, so then what we are trying to do is trying to learn a non-local operator surrogate from as a homogenized model. So for that sake, we developed the so-called non-local operator regression approach. So here is our working assumption. Here I still use the example problem one as to show that. So firstly, we try to collect data from, like, say, high fidelity simulation or from experimental measurements. So basically, like, say, you apply different loading, you have the responses of the material, like different, the forcing turn and the kind of the material displacement field. And then from this high fidelity simulation or the measurements, then what we are trying to do is we try to learn a non-local kernel K from the data such that our non-local solution, our non-local equation can act as an effective surrogate at a much coarser scale without resolving all those small interfaces layers. And then hopefully we can use this non-local surrogate model because it's at a much coarser scale, so it's more efficient. And then we can use that in like more challenging prediction tasks. So for example, a much larger domain or maybe a much longer simulation time and so on. Okay, so now for this problem, what we are trying to see is just a non-local kernel from data. So then let's put that into optimization based based approach. So here we can write that into a 3-step recipe. First we collect measurements and then we try to parameterize the kernel. And then here we assume that the kernel can be written as a linear combination of on some basis kernels. And here the linear. So then we just try to optimize these coefficients. That is the CM here. And then we optimize that with respect to the residue. So here the first residue is the loss, and then we can also have a regularization term, which is represented by R here. And moreover, we can also solve if we have the solvability of physics constraints, then we can also apply that and then try to try to solve a constraint optimization problem. So by doing that, we hope that we can decrease the reliance on the lab testing.
Yeah,
okay.
Just sorry,
go ahead.
Clarification. Because the solution is time dependent, but the data UXI there's no time there, or just you assume it's steady state, or
Oh, that's a great question. Yeah, sorry. For this particular problem, yes, you should have a U dot here. So yeah, sorry. Here I try to write it into a more general form, but for this particular, for this kind of what I should say, the dynamic problem, yes, there should be LU minus F minus U dot.
Oh, I see. But the data D you have, I assume you also have is UIX and T. Is that right? Or just the
right. Yeah, you are right.
I see. Okay.
Yeah. Sorry. I think here I should probably put the T here.
I got it. Thanks.
Yeah. Thanks. That's a great point. Yeah. So and then from there, let's try to. There are 3 key integrants in our development here. So now I'm going to explain that one by one. So the first one is, well, we can actually, we impose to use the solvability and the physical constraints. So then it can be applied through basis function design. So basically you can try to put the constraint and try to reduce some degree of freedom of the CM here. And it can also be applied as a penalization, so something like the regularization term here. So then, here for this application, I'm not going to emphasize too much on this physics constraint, but I will leave that to the next one, to the neural network one. But our general observation is by applying this physics constraint that the model, the prediction, the model is actually going to be more generalizable, especially to the prediction tasks, which is out of the distribution of your training. So for example, if I train on a maybe shorter bar, I want to do a prediction on a much longer bar, then this physics constraint helps a lot. Okay, so then the second key integrant, I think I also talked about that a little bit before. So that is, well, we try to model the kernel as a continuous function. We learn the functional form of this kernel. So so the previous work and also like say the neural network usually focus on these parameters. So, but here we are trying to learn the functional form of the kernel. So that is the first key to kind of make it possible to talk about the convergence of the estimator or the kernel itself, because then the kernel is basically a function. So you can refine the resolution and then try to see, the resolution of the observation and also the resolution of this kernel, and then try to see, does that really converge to maybe the ground truth or the optimal you are looking for. But that's not enough, as we are going to see soon, just by parameterizing the kernel to a functional form to make it convergent. Actually, we need something more. So actually, we are going to show that, well, the regularization term is also very important. Otherwise, the inverse problem is going to become ill-posed as the discretization size is becoming smaller and smaller. So that means if I try to refine my resolution here, if I'm trying to provide my data on a finer resolution, then kind of contradicts our intuition. Actually, the inverse problem is going to become more and more ill-posed. So how do we resolve that? We need to introduce a proper regularization term. So here we introduce the so-called the system intrinsic data adaptive reproducing kernel Hilbert space, or CRKHS regularization term. And then we can show that after we use this regularization term, then the problem becomes more identifiable and also more especially helpful when there's noise, becomes more robust to noise. So now let's try to see what goes wrong when we are using when we are using the traditional regularization term, like a classical Tikhonov regularization term. So here, firstly, let's try to look at kind of a synthetic data problem. So here we assume that we have a ground truth kernel, and we have like two pairs of U and F corresponding to this classical the synthetic ground truth kernel. And this ground truth kernel, for your guys' information, that's the fractional kernel. So then if we try to use the classical Tikhonov regularization term, so for example, here the small L2 norm or like the large L2 norm. So here the small L2 means you see the parameter C as a vector, and then you just use the vector L2 norm for that. And then the large L2 norm means because my kernel is actually function, so you just try to measure the function L2 norm of the kernel. And then what I'm showing here is basically how the kernel is going to, how the estimator is going to converge to the ground truth kernel. So here the x-axis, from left to right, is the kind of the data mesh resolution. So basically from relatively fine to relatively coarse. And then here the blue line shows the L2 error to the ground truth kernel. And then the dashed line, so the dashed line is the results that when the data has some noise, and then the solid line is the results when the data, it's clean. So here we can see that when the data is clean, then these two classical Tikhonov regularization terms still kind of looks fine. If you try to refine your observation resolution, your estimator is somewhat like convergent. But however, if there is noise in the data, then things go wrong. You can see it doesn't converge anymore. So when you try to refine your resolution, then the error doesn't decrease. You are not getting the ground truth kernel. So why is this happening? Well, so basically we are trying to show that, because we really need to find what is the correct function space of the identifiability. So here we have been the message is we have been showing that the identifiability space of this non-local learning problem is actually characterized by this reproducing kernel. And then beyond this space, the inverse problem is strictly undetermined. And then moreover, based on this space, we can further show that, the eigenvalue of our integral operator actually is going to go to 0. So therefore that means when you try to change the resolution, refine the resolution, then it's more kind of getting closer and closer to the continuous problem. So that actually makes your inverse problem more and more ill-posed. So that's why when you are changing the resolution to get some convergence, it's more and more important for you to use the good regularization term. So now we propose to use because now we have identified our correct space. That's our CRKHS space. So then we use the norm in this space as our regularization term. And let's try to see how how the estimator perform. So here is the result, still that fractional kernel. So we can see that now we can finally see that as we try to, even for the noisy data, as we try to refine our observation resolution, then we do have some convergence to the ground truth kernel. Okay, so now you might want to argue that, well, here I'm just showing, like, say, well, the converging to the ground truth kernel to the, to some synthetic data problem. What about your real world problem, right? So for example, what about my heterogeneous? And maybe another argument will be, well, maybe my kernel, although my kernel is not identifiable, I'm not learning the ground truth kernel, but maybe, the effect, when I try to use this kernel in simulation, the effect is the same. But now here, let's try to see what about in our real world problem, especially, just our example problem number 1. So here we are trying to learn basically this non-local surrogate to model the kind of the stress wave propagation in a heterogeneous path. So to generate the training data, we have exact direct numerical simulation solver which resolves all these small interfaces and therefore very expensive to compute the velocity and the displacement. So therefore our training data set has the 3 types. So the first one is, so basically the first one is the oscillating source. You have a different source term, and then you have the plane wave, 2 types of the plane wave data. So here you can see these 2 types of plane wave data, they are like you are applying a velocity on the left end of this bar, but this velocity just have different profile. One is cosine and the other is sine. So intuitively, we would expect these 2 types of plane wave is going to give us the same result, the same learning result. And moreover, for the training data, we focus on relatively short time from 0 to 2 and a relatively short bar. So the bar length is 100. So now let's try to design some experiments. So basically we design 3 types of the experiment. So the first experiment is, well, basically we try to use the first type of the plane wave data and the second type of the plane wave data respectively. And we want to see how sensitive is our inverse problem to the data. And then moreover, we are also interested in the convergence behavior of our estimator. So therefore, we try to refine the resolution scale, the observation resolution, and see if our kernel is really convergent. So here is the results of our 3 experiments on the 3 types of the regularizers. So here the first row, I show the results of the learned kernel. And then the second row, I show the results of the group velocity. So basically the group velocity characterize, well, what is the dispersion behavior of this surrogate model when you have different frequency range. And here I also compare that with the ground truth. So basically the dispersion property from the direct numerical simulation. And the last one is what we call the physical stability. So intuitively, like all this, it has to be this omega squared, it has to be larger than 0 to guarantee that this model is physically stable. Otherwise, you just, the numerical simulation of that will become, will diverge. So yeah, so now let's try to see what's the behavior of our 3 regularizers. So we can see that firstly, only from the first row, we can see that only our CDA-RKHS can give consistent kernel for all 3 types. And then also, why is that important? We can see that from the third row. So here we can see that, well, if you are using the room regularizer, then at least for some of the data, or like say some of the resolution, then the model is going to become stable. You just couldn't use that for the further prediction task. So that's the importance of using the right regularization. So now maybe let's further try to, so here this is just a qualitative comparison. Let's also try to do some quantitative comparison. But for this problem, we don't really have the ground truth kernel. So to quantitatively characterize our learning effect, all we can do is to compare that in a prediction task. So now we consider much longer bar, much longer simulation time, and also subject to a different, like the loading along this path. And now let's try to compare our simulation on a kind of a time which is 50 times longer than the training, and then compare that with the direct numerical simulation. So here we can again see that, well, only the theta RKHS, firstly, it gives us the smallest error of the predicted solution, and moreover, it's kind of decreasing when we try to refine the observation resolution. Yeah, and maybe because of the constraint of time here, I'm going to go fast. And moreover, we also even challenge ourselves more. We try to throw our surrogate model to a really, really long-term simulation when the time is up to 600. So that is already 300 times longer than our training time. So still, we can capture the wave front pretty accurately. Okay, so yeah, so now I think as Professor Lai has mentioned, well, that's the surrogate model is kind of more maybe restricted to like a homogenized material response or homogenized system behavior. So what if my system behavior is non-homogenized? It's a heterogeneous one. So that's our second type. We call the neural operator. So basically, this one, now we cannot simply neglect the kind of the micro. We cannot kind of homogenize the microstructure anymore. And then in this problem, we are still interested in learning the material response. How can we do that? So what here we propose to do is we propose to basically integrate the underneath, like say the model finding, the microstructure identification, and also the solving procedure to find a solution operator directly. So that means, well, what I try to build is basically a mapping from the loading that can be like say boundary condition, can be the external loading, can be different microstructure depending on application, then to your solution, to your material response directly. So this material response represented by U can be the material displacement, can be the damage field. Okay, so how do we do that? We propose to use the neural operator learning approach. So here, so this is a recently very popular like the area, and there are like many groups like working on that. So here I'm just listing a few representative groups. And then for the neural operator learning, then basically what we are trying to do is we assume that there is an underneath governing equation, but we don't really know what is this governing equation. And then you can see this governing equation is characterized by a kind of a very general operator L, but this operator L can be any form, can be hyperbolic, elliptic, or nonlinear, anything. And then what we are trying to learn is the operator that maps from basically the loading from the microstructure boundary condition to the solution directly. So this approach has like say multiple advantages setting, and then so basically maybe you become, let me go to be quick. I don't want to hold everybody late. So how do you, and why this neural?
Take your time, no worry. Okay.
Already.
Yeah.
Okay. Thank you, guys. I think I should buy you guys dinner if I'm there in person. So, okay. So basically, why this neural operator is related with my non-local operator? Maybe you raise this question. Okay. So let's try to see from our PDE 101. Let's consider elliptic equation. So in our PDE 101, how do we solve the elliptic equation? Well, you can write your solution as an integral of a Green's function and together with the loading term, right? Then when you have different loading term f, then you get different solution just by using the integral of the same Green's function. So then the Caltech group, they try to from here they try to propose to parameterize the Green's function as a neural network. So that means, well, for the L's layer, to get the L+1 layer update, so the layer feature H here, they propose to apply the action, basically the activation function on an integral of this layer feature at L, and then with its neighborhood, and then together, and then plus a local linear transformation. So here, all the trainable parameters, I highlight that by blue. So then starting from there, then you might have different ways to parameterize your Green's function. I mean, this non-local kernel here. So for example, you can parameterize that as MLP, then you get the graph kernel network. We also have some work along this trend, but here I'm going to focus more on the second type. So when you try to parameterize this kernel as a convolutional type, so then you end up getting the so-called Fourier neural operator, or FNO in short. So why we want to write that as a convolutional shape? Well, that's because then you can rewrite your integral term using the fast Fourier transform. So that will make your evaluation of this integral term very, very efficient. So then, so here what I'm showing is the architecture of the original, the FNO, the Fourier neural operator. So basically, when you have your input function, which can be A here, you go to the lifting layer. So basically, and then you are going to have basically the feature function h, and then your feature is going to go through like t numbers of the so-called Fourier layers as shown above, and then you go through a projection layer, so maybe like something like a pooling layer, and then go to your output function. So then here, what I'm trying to emphasize here is, well, it can be shown firstly, this FNO can be a universal approximator to operators. But however, it requires you that, well, for each of the layer, you have to use a different parameter. So that's why you can see all these learnable parameters here. I highlight that with L because that changes with layer. So from our the non-local operator regression approach, we have already been seeing that if we're only learning a non-local operator, then we already have some identifiability issue. Right. So, but if we are using a neural network, so thinking of if you make your layer deeper and deeper and your number of parameters is increasing with that, then these things can become even more severe. So how is that like? Let me try to show you guys an example, a simple benchmark problem. So this is a 2D Darcy's equation. So basically that represents basically trying to solve for the pressure field of a porous media material. So here A is the diffusivity. So basically the microstructure of this porous medium. U is the displacement. U is the pressure field. So that's the solution we are looking for. And then we are trying to learn basically the solution mapping from this porous media to this microstructure to the pressure field from 1,000 pairs of the observations. So here I'm showing two exemplar microstructures and then the corresponding ground truth solution. And then on the third column, what I'm showing is the FNO when you are using 4 layers. So you can see the FNO solution is somewhat similar to the ground truth when using 4 layers. But if I'm using more layers, what will happen? Well, so that's the last one. So when I'm increasing the layer to 32, then things didn't get better, so even go wrong. So you can see the solution is totally off. Why is that happening? Let's try to see what is the training error and the test error change when you try to increase the number of layers. So here the x-axis are the number of layers. When you increase the parameter from layer 1 to layer 32, then you have the number of parameter, of course, increase like drastically. And then the dashed line shows the results of the training error. You see the training error keep decreasing when I increase the layer number from 1 to 16, but that's not true for my test error. So that means, well, there is some overfitting issue happens here when you increase the layer number. And moreover, if you try to further increase the layer number, then of course the neural network becomes too deep, then you start to suffer from the vanishing gradient. So not only the training error, not only the test error, even the training error becomes really large. So how do we resolve that? Well, let's go back to our elliptic equation. To our PDE 101 equation. So in our numerical PDE 101, how do we solve this problem? Well, basically we can use either finite element method or finite difference method to discretize this PDE, right? So then you have like multiple degrees of freedom. And then so then this degree of freedom forms a vector u, and then you substitute this u, you end up getting an implicit equation for this vector u. This implicit equation can be awfully nonlinear. So then how do you solve this nonlinear equation? Well, we use the iterative method, right? So one of the basic one, of course, for example, is the Newton-Raphson method. So then if we try to expand the Newton-Raphson method, this is how we solve for that. Well, from the iteration L to iteration L plus 1, then basically we subtract an increment of the iteration L, and to get the iteration L plus 1 solution. So how is this increment looks like? If you try to zoom in, it's actually an operator, but this is an autonomous operator. It only depends on UL, only depends on your iteration L solution. And it can be nonlinear, but it's autonomous. So that actually gives us inspiration. So basically, well, firstly, we propose to, instead of parameterize the layer update, let's parameterize the increment of the layer update. And moreover, and then if you try to see the layer update kind of like an analog as the iteration L here, then we propose to use the autonomous operator. So basically that means the operator should be the same for each layer. So therefore they share the same parameter. All the layers share the same parameter. So, okay, so by doing that, that actually also gives us can allow us to use another technique. So basically, if we try to further see the H here, the L here as corresponding to time step. So then if you try to subtract the H XL to on both sides and divide by some time step, the time step equal 1 here, then we can see that this layer update equation is actually analog to the discretization of a time-dependent nonlinear ODE. And then that means when I get my layer like deeper and deeper, using more and more layers, that's corresponding as I'm actually using smaller and smaller time step size. So, and also they are actually, so therefore, and intuitively we can guess, well, then this nonlinear ODE solver, it should be get more accurate. And moreover, they share the same parameter because you are solving the same ODE. So therefore, the parameter we learned from a shallow neural network can actually be reused as for a deeper neural network, and or it can be used as a good initialization guess, the initial parameter to make the convergence faster. So this technique we call the shallow to deep. So basically, you can firstly train a shallow neural network, and then for when you are trying to initialize a deeper neural network, then basically you can try to use the same parameter and as an initialization. So here we can see that it can give us a faster convergence, especially in a deeper neural network. So now putting everything together. Yeah, sorry.
Sorry. So does this have to be time independent, or it still can be time dependent? Because
that's a great question. So the time here, what we mean is actually really just analog to the layer. This is the real time. You can think of that as actually a pseudo time here. So, but however, independent of this architecture, actually you can apply this technique to a time-dependent problem. So for example, you can think of your input function is your solution from the last time or maybe previous several time steps, and then your output is your solution for the next time step. Then you can also formulate that for a time-dependent problem. But the time here is not a real time. It's just corresponding to the layer.
Sure, but if your ODE is like, if your right hand side of ODE is like time dependent, then if you still use the neural network to solve that one, then each layer, that weight, it cannot be recurrent, right? It has to be each layer, the parameter should be different. So which means if you understand like 3 layers, and you can now apply to like 15 layers.
Yeah, that's a great question. I think that depends on what is the property of your ODE. If your ODE is an autonomous one, then I think that, but if it's not autonomous, no, you cannot do that.
That's sort of my question. Yeah. Thanks.
Yeah. But here it's, I mean, the time is not the time. The time is the yeah. Yeah. But thanks a lot. That's a great question. Yeah. So actually, also because it's autonomous, so we can do this trick. Otherwise, we cannot do this trick. Yeah. So now let me try to summarize how our implicit F&O looks like. So basically, firstly, we parameterize the kind of the layer update, and also we use the same parameter for each layer, and then basically the key feature, the key contribution here is because firstly each layer share the same parameter, so that actually reduce the memory allocation. I mean, kind of like I greatly reduce the memory allocation, especially for the deep layer neural network problem. And moreover, it also helps to resolve the overfitting issue, as we are going to see in our example soon. And also because it allows the shallow to deep initialization, so that helps to resolve the vanishing gradient issue. So now I think we go back to the question that Professor Lai asked it at the beginning. Well, is this a universal approximator, right? So at the beginning, I emphasized that F&O, you have to use different layer parameter for different layers. Otherwise, it's not a universal approximator. What about IFNO? We have reduced so many parameters. Is that still a universal approximator? The answer is yes, as far as you are trying to find the solution operator for a good hidden PDE problem. How do you characterize good? Well, that means as far as my PDE problem, there exists a fixed point formulation that is convergent. Then I can show that for any desired accuracy, I can find a parameter set of my IFNO such that my IFNO can actually achieve the desired accuracy by using like a sufficiently large number of layers and also a sufficiently large number of the feature dimension. So therefore, that means it's a universal approximator, but only to good PDE solution problems. So hopefully I answered Professor Lai's question. So, okay, so now let's go back to our original the pitfall of the original F&O. How does our IFNO works? So here, the red line shows the results of IFNO. So firstly, you can see the number of trainable parameter, it doesn't change when you increase the number of layers, right? And of course, because the number of parameter is smaller, so therefore the training time is also much smaller. And moreover, if you try to see the training and the test error, you can see not only the training error, but also the test error is decreasing like autonomous, like monotonically. So actually, when the layer is larger than 2, then we already beat the original F&O. So I think because of the constraint of time, I'm going to skip my example problem number 2, but let's try to kind of jump into the more challenging problem, the experiment problem directly. So this is again my heart valve tissue leaflet modeling problem. So this is actually a heart valve tissue, and it's actually mounted on a kind of a device that in my collaborators' wet lab. And then after a preconditioning protocol, we perform 7 different testing protocols. So this different testing protocol, actually, that means, well, basically the stretching ratio has different, so basically the stretching has different ratios between the first Kirchhoff stress in the X and the Y directions. So this one we are interested to see is, well, from the boundary loading. So basically for the loading applying on the boundary of my leaflet, then how can I predict the interior response? So basically the material deformation of the interior. So let me firstly try to do a simpler task. So I mix all my 7 different testing protocols together, and then I take like 20% of the loadings as the test, and then the rest will be used as the training. So in this scenario, basically, we can, although the test samples are not in the training the neural network has never seen that during the training. But however, it's in distribution. It's covered by the distribution of the training data. So in this case, we compare that with the classical, like the phenomenological model, which we call the Fong's model, which neglects the material heterogeneity. We can see that, well, our if model can actually decrease the error by almost 1 order of magnitude. And then why it can do that? Let me try to zoom in a little bit. So here, I'm actually trying to show you one of the representative samples. So here, the first column is the ground truth, second column, if no, third column is the full model. We can see that, well, basically the error actually really comes from that. The if no can capture the heterogeneity, it embeds the heterogeneity in its parameters. But the full model, the classical model, it neglects the heterogeneity. So you can see the error kind of like centralized in the middle. So now let me try to increase the challenge. So basically we know that neural network usually it might suffer from the generalizability, right? So especially when my training distribution is different from my testing. So here we are trying to study what about the out of distribution prediction task. So remember, we have 7 different protocols. They have different stretch ratio on the X and the Y direction. So here I'm using 3, so which are highlighted by red as the training, and then the other 4 as the test. So here you can see the test is really, they are not covered in the training protocols. So then now let's try to compare our if no and the classical form model. So in this case, you can see our if no actually deteriorates. It's actually the test error is like a similar scale as the Fong's model. They are both like 17%. So yeah, so now, well, how can we try to improve that? Let's try to see how does the error looks like. We can see that the error, it's really, the if no behaves worse than the Fong's model, mostly in the small deformation cases. So that inspires us the idea that, well, why it behaves worse than the Fong's model in those cases? Because it doesn't know the physics. It doesn't know even very basic physics. So for example, if my material status is that still there's no loading on the boundary, then there should be no response, no deformation. So how can we correct that? Well, we can design physics the constraint into that. So therefore, we propose to kind of infuse partial physics knowledge into that. So here we are imposing the no permanent deformation assumption into that, meaning that when there's no loading, then my material shouldn't deform. So I add that as a penalization term into the training loss, and then put everything together. Then finally, we can see that, our if no gets improved, especially in this small deformation region by 1.5%. And that can also be seen as in our Exemplar, like the sample. So it really improves, especially in the small deformation samples. Okay, so yeah, sorry for the delay and sorry for the accident. So yeah, let me try to go to my conclusion. So what we talk about 2 non-local operator learning techniques, one for homogenized modeling task and one for like heterogeneous material modeling task. And one of the repeating thing is by learning a continuous kernel for these learning tasks, then we can achieve like resolution independence. We can actually achieve like we can actually sometimes even achieve the convergence and the better like the fitting property of the neural network of the data-driven model. And moreover, by imposing partial physics, we can also improve the generalizability. Okay, yeah, so sorry for the delay. I think, yeah, I want to thank my collaborator, my funding agency. And if you are interested to, for example, to try our model or even try our data, so here is the GitHub link.
Okay, very, very good.
Sorry, yeah.
Maybe any questions?